So hello everyone, welcome to the first office hours working session. My name is Dhruv, I'm a data scientist at Comet.
And my name is Michael. I'm a machine learning engineer at Comet.
So as part of our office hours series on standardizing the experiment, what we are trying to do is Michael and I will be hosting a number of working sessions where we will be going through somewhat of a real life ML problem, and we will be building a model, going through the individual steps of the standardization process. And along the way, we'll be showing you how you can use Comet, sort of different steps in the process to structure your workflows, organize your experiments, and in general, collaborate with your data science or machine learning team. So we have this Git repo here, which will be the basis of like our entire project. We have been given a business objective to maximize the traffic that we receive, that our company receives from a post on Hacker News. So our requirement right now is to create some sort of model that can predict the performance of the post. Before we get like really into the whole modeling aspect of this whole process, let's take a look at some technical requirements that we've set up for this project. These are just ground rules that like help Michael and I like collaborate a little better and just set expectations for what data sets we'll be using, how we should be structuring metadata, how we should be logging our experiments. And it's good to just establish these ground rules before we get started so that there's like no confusion down the line. So we're going to be using artifacts. If for those of you that don't know, artifacts are a tool from Comet that help you version data sets and all sorts of other data assets. What we're going to do is we are going to be using the Hacker News dataset from BigQuery, and it's for the years 2018 to 2020. What we're going to do is we're going to use roughly the posts from 2018 to 2019 as our training data set, and the post in 2020 as our test data set. So before we begin, let's go through like these artifact requirements. Without getting too much into details about artifacts, we'll leave a link in the description below if anyone is interested in finding out more about them. But what we're going to do is artifacts have metadata associated with them. And what we're going to do is establish some sort of structure for this so that when we fetch the artifact in our code, our training code, we have some sort of expectation of what the structure of this metadata will be, and then we can use it to annotate our data sets, make sure that we're passing the training data set correctly and the validation data set correctly to our models, and we know how and where to save these files. So basically the metadata and the artifacts will have a file name. It's a dictionary with two fields. So the first field is the file names, and then underneath that, the two fields are the train and the validation split. So under the train split, you have the name of the train data validation file, so the train data file, and under validation, you have the name of the validation file. Our data will be saved as a pickle file. And then the next field that we have the columns of the data set. In this dictionary, we will have each field in this like subdictionary will be the name of the column in the data set, and the value will be a description of the data in that column, just so that there's like some context around what sort of data you're pulling from the artifact. Let's take a quick look at this artifact. In your Comet workspace, you can find artifacts in their own dedicated tab. So as you can see, we have this public artifact called dataset. Go into that, we can toggle a description. So it's like the Hacker News dataset for the years 2018 to 2020. And then we also have the version. So since I've only run a simple uploading script for the version, so this is version 1.0.0, and it automatically gets tagged with an alias, which is like instead of using a version number, you can use an alias tag to refer to this data set. So we go into that version, we have a train file and a validation pickle file, and then in our metadata, we have the file names. So we know that the train split means that you should be loading in the train.pickle file, and then for your validation split, you should be loading in the validation pickle file. And then we have a series of columns for the data in this like data frame. So the title is just the post title on Hacker News. URL is the URL if you're linking to like an external site. Text is any user submitted text for the post. And then by is just like the user ID. Score, this is basically the target value that we are trying to predict. And time is the Unix timestamp of the post. And timestamp is like the date time format timestamp. And I think the type is the like whether the post is a story or a comment. All these data sets, all the data in these data sets, they just post with title and text. We are not looking at comment data for this project as of right now. And then, so because we're not looking at comment data, this parent field is also relevant because all the posts, none of the posts will have a parent. They're all like top level posts. And descendants is like finally the number of comments, which I think will be a little difficult to figure out at test time, but let's see how we deal with that. Cool. So let's go back. Then finally, just some housekeeping around our experimentation requirements. So when we are running an experiment, one of the things, and we'll show this in a minute, one of the things that you can do with Comet is log most training scripts or dataset profiling scripts or fetching scripts that we use in machine learning you tend to pass in like command line arguments. So Comet can automatically pass these arguments. For any experiment that we run, we're going to pass in a command line argument called message, which is the function of this is like similar to a git commit message. And then we can organize our project by these messages. So like in the future, if we want to just quickly figure out all the things we tried, we don't have to sort of run more like numeric queries. We can just look at the messages and get some intuition for what we've done. And then the second rule is if we are logging predictions, like model predictions to our experiments, like we will save them as predictions.csv file and log them to the experiment as an individual asset. And then finally, trained models will be logged to Comet using the log model method as opposed to the log asset method. And the reason for this is if you log a model using the log model method, you can add it to the model registry, and that sort of makes it globally available to download without actually having to find the exact experiment that the model belonged to. So let's take a look at the structure of this repo. So sort of to organize our repo, like just so that there's some organization, it's like a fairly opinionated guide. Would you say, Michael?
I would. And I think we're shooting for a happy medium here in the way that we're setting up this repository. We know that as our project grows, I guess, in complexity, and as we start building out more candidate models and so forth, we know that we're going to want to modularize our code a fair amount. And if you look at industry scale, industry grade repositories for big popular machine learning models, you'll often see like very complicated and sprawling repo layouts. But broadly speaking, you see something like this, right? Where you have some stuff that's for dealing with a data set, some stuff that's for computing metrics, a directory with scripts in it, or maybe just for us, a single script where you define models, a script for that you would call to make predictions and so forth. And of course, like a training script and all that good stuff. And then on top of that, so that's all kind of living in this source directory under HN predictor. We've also got a directory called data. So that's where we'll be storing the data set, and another one called assets, which I believe we're using for logging like those prediction assets, for instance. So this is a way for us we actually decided even before we started writing any code that we were going to take this, sort of scaffolding for this project. And that's something that I would really recommend when you are starting out a new machine learning project like this, especially if you want to ensure that standardization as you're continuing to build on your work. Basically, having a clean structure to build on top of is going to be really helpful for that.
Yeah. And I just want to add that we do have maybe some not necessarily super standard scripts here, like profile data frame, because this script is essentially, we're trying to be lazy with our EDA. We're going to be using pandas profiling. I mean, we're using data frames for this data set because it's like a tabular data set. And then rather than sort of build some notebook or maybe more sophisticated analysis script to get some insights from the data, sort of just to get an initial feel of what's happening and not necessarily diving into deep in the weeds. We're just going to create a simple script that will ingest the data frame and run the pandas profiling library on it, which is like an automated EDA library. And it will generate a report, which is an HTML file that we will log the Comet. And then we can use a bunch of tools inside our Comet project to just quickly look at the data and sort of define our strategy. So we're on our machine. We've sort of cloned the repo, just walk through the structure. So one of the things is when you're running experiments and configuring experiments, you have to, like Comet has the concept of workspaces and projects. So we want to log everything. And if we were like manually setting our project name and our workspace for every run, like we're bound to make like typos or like some sort of mistake and then log something to maybe an unintended project. So just to help with the housekeeping, we defined this Comet config file. So in the Comet config file, we basically have certain fields. It's an INI file that you can specify the workspace and the project name that you want to log to. And then you can also like turn on and off certain things for the Comet auto logger. So in this case, we're going to log all our Git information so that we can leverage some of the Git metadata and Git patch tracking features in Comet. So that's the Comet config file. Let's go into the data file. The data file basically has, it's like really just using pandas and pretty much nothing else. So a very basic like load data method to use in the pickle file given the fetch dataset artifact. I mentioned earlier we were using artifacts for fetching our datasets. So what we're going to do is like we've defined this method that given an artifact name and a version and some sort of output directory to save the artifact, will pull that artifact from Comet and download it to that directory. And when we go into like the profiling script, you'll see like how this path is set. And then finally, we have the profile data function, where you can pass in a list of data frames and we will automatically use the built-in data frame profiling method, pandas profiling on the data frame, and log the report as a HTML file to the experiment. And there are like certain flags you can add to this log data frame profile method. Like minimal is basically if you have a very large data frame and you don't necessarily want to run all the, I think pandas profiling runs like 4 or 5 different types of EDA operations, like correlation matrices, feature interactions, like that kind of stuff. Most of those, you can just specify minimal as true. And then finally, because we've already, if we did want to log the raw data to Comet as a data frame, we have that option. But in this case, we're just going to default to false because we've already logged it as an artifact. So let's go to the profile data frame script. This is where we configure our dataset path. We mentioned earlier that all the data that we're going to download is going to live in this like top level directory. So we're just like setting a default for our data path. But then because we're using an environment variable, you can configure this to wherever you want. So you can store your data in some other folder, any path in the file system. And then just the arguments that we're going to be using, everything that we pass the profile data frame methods, like the artifact name, version, will default to latest. So the script will always fetch the latest version. A flag to whether or not to profile in using minimal mode, and then a flag to log the raw data frame. And finally, because we discussed this in our experiment setup, we were always going to be using a message argument just to sort of organize all our experiments nicely. You can see that where we create in the script, we create the Comet experiment, we add a profiling tag so that we know that this experiment ran a profiling script. We have the fetch data artifact function that downloads the data to our local directory. We run the load data function to load in the individual data sets. The split name is basically whether or not that data set belongs to the training or validation split. I can go back to data.py just to explain that. So the output of like the fetch data set artifact will be a dictionary where the key is the split, so whether it's the training split or the validation split. And this is what we're fetching from the metadata from the artifact, and the value associated with this key will be the path where the artifact asset was downloaded. So because we know what the file names are, we can construct this path and then return it back to our profile data frame method. And that's how we load in. We go from a pickle file on our file system to a data frame in our code. And then finally, we will profile the data set. So without any further ado, I think I can just go ahead and profile this data set. So let's see. Oops, source. And just a heads up, I created this virtual environment and installed the requirements like beforehand, but we can go through the requirements.txt file, but it's like really just Comet, pandas, and pandas profiling. So let's do Python, profile data frame. So we don't want to use minimal. So let's do false. Actually, that's a flag. So we have the artifact name. The version is already auto-save. What other arguments do we have? Yeah.
Well, we need our message, and I think that's the
Oh
only
yeah.
other
Well, I guess,
non-default.
yeah, I guess everything else has defaults. Profiling, and data set. Cool. I think that's it. Good to go. So you can see Comet is now downloading the artifact, all the assets in the artifact from our workspace. It's been downloaded, and now we're running the profiling script. Yeah, I guess there's like 19 operations that it's going to run. So this might take a little bit of time. Great. So we have run our profiling, and now we have an experiment that is saved to our project. So let's go do this. So this is like the experiment view of our profiling experiment. So as you can see, we've logged our message as a hyperparameter, and then also the artifact name that we used. Additionally, you can find like the artifact that was used to like in this experiment, like under the assets and artifacts tab, like right here. And you can also, because we didn't really produce any or save any artifacts from this experiment, you can sort by whether or not the artifact was used as an input to the experiment. So in this case, it's like it was used as an input and we switched output. And then if I click on this, it'll link me back to the artifact section of the workspace. So before we like really do anything, let's take a look at this experiment and do a little bit of housekeeping. In Comet, you have the option of configuring your experiment table any way you like. So we picked using and you can save these configurations as individual views. So what I've done here is taken a group by operation, and I've grouped all the experiments by message so that it's just easier to just read what was done rather than try to interpret what was done from the parameters or metrics that were logged, or even the source code files, depending on how you're organizing it. And then I save the view as message. So if I want to toggle between views, so now I'm in the auto-generated view, basically has a very simple table just showing all the information about the experiment. But if I want to switch back and see what was actually done in however many experiments based on my messages, I can just change the view. So now let's go to our panels section. So I haven't added any panels yet. So what I'm going to do, actually, let me go to the experiments, talk about what we're going to do. So in the assets and artifacts section, we have HTML files in our experiment. One is for the validation dataset profile, and then the other one is for the trained dataset profile. So these are HTML files, and what we're going to do is they have all the information about like dataset distributions and target distributions for these datasets. And we are going to use some Comet panels to do our EDA. So like first, we can just add our panel. So we go to the public panels. All right. And then we'll look at HTML. We have this HTML asset viewer panel. We'll just add it. And since we have two data sets, two profiles, let's add another one just so that we can easily compare them. There it is. Okay, so let's edit the layout so that we can see everything. That. Expand this a little bit. Okay, done editing, and then let's save the view. Have this old view. Yeah, okay. Created this view called data frame profile. Basically has these two HTML asset viewer panels, and then we can switch between the asset files like up here. This one is for the train asset viewer. Let's go add the validation set asset view, and we can see all the variables. We can just jump down. So we have things like the title. So we know for a fact that the title will be have high cardinality. There's missing values. URL again, same thing, high cardinality. Same with text. We haven't really done any pre-processing or like we haven't touched any of the features. Just raw data set. Dead looks like Michael. It looks like there's nothing in dead. Mostly missing. It's dead.
Yep.
And then finally, we have the feature or sort of the column that we care about, which is score. So there are like some high correlation flags in score. We'll dig into what these mean later, but let's toggle the details in the training set. So we have these descriptive statistics and quantile statistics. You can notice that the minimum value is 1, happens automatically to any post on aggregate, right, Michael? Like if you just submit, you get 1 vote. So
Yeah,
that makes
so we're
sense.
starting at 1, and I want to point out a couple other things here. You'll notice too that looking through the quantiles all the way up to the first quartile, we're still at a value of 1. So at least a quarter of these Hacker News stories never get any additional upvotes aside from the sort of default one. And we're seeing this distribution among the scores of these Hacker News stories, where there are, for the most part, very many stories with very low scores and a couple of them with higher scores. That's going to come into play in a few minutes when we talk about how we want to model predicting that target variable.
Yeah, so we can just take a jump and take a look at the value. So like 40 something percent of the data set has a value of 1, and then it basically just drops off, right? Like it seems like it's harder to go from 1 to 5 than it is to go from 5 to 10 or 10 to whatever. The jump seems like more reasonable. So like to me, it feels like you need some sort of initial kind of velocity to take off, and like what is contributing to that, I don't know. It could be you get your friends to like just give you a bunch of upvotes, and then maybe that maybe it's a post title, maybe it's at the time of day. There's a lot we can do here. We could frame this like as a regression problem. What do you think, Michael?
Yeah, I think that there are arguments for either way, or multiple ways of framing this problem. We might think about this as regression, or we might think about it as classification, for instance. We might take these, broadly speaking, continuous values in our target of these scores, and we might think about binning them, or just putting them into, maybe defining like some threshold above which we say that's enough points, right? We want to predict whether or not a post will get at least a score of 10 instead of, so that's one way. We might simplify this all the way down to binary classification. Will this post, or will it not, get above some score threshold? Now, why might we do that? Again, for one thing, because of the way these scores are distributed, it might not be super meaningful to try to make a prediction, about the precise number of points that we get. We might be more interested in a downstream effect of the number of points, right? Is this post going to get enough points to be viable in some sense? Is it going to get enough points to be a trending post, or to be among the top 10% of posts, or something like that? And we can look at regression versus classification and say which one of these is ultimately going to match our applied intentions and the way that we're communicating with like the other stakeholders in this project. It might be the case that for our sort of internal clients for this project, it is more useful for them to say, if I have a couple of different potential headlines, maybe this one is more likely to succeed, and we can communicate about that in a quantitative way, I think a little bit more appropriately as classification. Or it might be the case that they really want that estimated number. So having a couple of different ways to frame the problem from a quantitative standpoint gives us more flexibility in how we communicate with the other people involved in the project. And it can sometimes help us to match our predictions onto how we actually use those predictions. So those are some thoughts on like regression versus classification here. And then we'll end up trying both of those types of models for this project as we get started.
Yeah, and I agree. Like, I don't necessarily think you need to get 100 upvotes to trend, just based on like how these scores are distributed. Like, it's very rare. Like, I think like, beyond like less than 0.4% of this data set has more than 10 upvotes. So like really the beyond 10 might be all you need to have an effective post. So I think you might be onto something, like maybe framing it as a binary classification. But yeah, let's consider both approaches just to get a feel. If anything, this whole series is about baselines. So we'll get like a bunch of baselines and then kind of figure out where to go from there. Before we do that though, I would jump into baselines. Let's take a look at the validation data set just to see if our distribution is similar, if there's anything weird. At first glance, it looks about the same. I think there's a difference in the maximums. Yeah, so the maximum is a little different, but like roughly in terms of missing scores, about the same. Details, right? So yeah, all the percentiles look exactly the same. Yeah, more or less. I think that just the 95th percentile is a little different, but I think it's like it's so unlikely that you might end up in the 95th percentile. Maybe maybe it's not like really that useful for us. Standard deviations look about the same. Variation, kurtosis is like roughly the same. Means are very similar. Yeah, anything else you can think of that would, yeah, and like the distribution also looks pretty much the same. Nothing seems that like the training and validation data set, it doesn't really change over time. So the distribution in 2018, 2019, and then versus 2020 has not changed. So like COVID hasn't really done much for the score distribution of these posts, although I'm sure that there will probably be a lot of COVID related posts in 2020 data sets. So that's something we probably have to consider down the line.
Yeah, and I actually want to take a second to talk about that really quickly. As you mentioned, like we're using 2018 and 19 as a training set, and we're using 2020 as a validation set. Now, we already know that there's likely like going to be an abrupt shift in the distribution of what Hacker News posts are about.
Yeah.
There are probably almost zero of them about coronavirus before 2020, and there's going to be an explosion of them in 2020. So that means that we are going into this expecting to have some distributional shift in the features of these articles if we're looking at things like the headlines or the text contained therein. But right now, since we're just focusing on our baseline models, like in a really strict sense, are actually not using features of the data. We're just seeing what happens if we only use the target. And so right now, that's also why we're focusing on just the target distribution. So I just wanted to mention that in case anyone had already kind of been thinking about this, issue of distributional shift between 2020 and the years, prior.